Welcome to lecture 21 of MCS 471, numerical analysis, or still more in particular, numerical linear algebra. So in this lecture, we will conclude our excursion into least squares problems. And this lecture is more on the application side. In a way, we extend the least square solving to nonlinear system. So far what we have covered are the solutions of linear systems with more equations than unknowns. Today we will look into nonlinear systems, extending Newton's method to the method of Gauss Newton. We will introduce yet another matrix factorization, the singular value decomposition. For the main reason also that we can use the singular value decomposition to check the local condition numbers of nonlinear systems, of approximations to solutions of nonlinear systems. The other application of the singular value decomposition is in the computation of the condition number of a matrix. So we have defined the condition number of a linear system, but we have not really addressed how the condition number should be computed. So the norm of the matrix times the norm of its inverse, that formula breaks down when is actually not applying when the matrix is not square, and it also not applies when the matrix is singular. So we will see with the singular value decomposition, we will have one better way to define what is the condition number of a matrix. In a sense, it's also the way how the singular value decomposition is computed is not really in the scope of this course, but this is where the QR factorizations come in again. But this is not in the scope of this course. In this introductory course, we end with the method of Levenberg-Marquardt. So in a way, this is an applications lecture. Many problems are never solved with one single idea. So in this lecture, we combine a lot of ideas, and the method of Levenberg-Marquardt combines Gauss Newton with the steepest descent. The steepest descent idea that we encountered earlier with the conjugate gradient. So this lecture falls a little bit in the middle of the course. It's a general lecture, an application lecture. So I will spend some time on Julia again, how we can compute with Julia. And also it's a lecture that ends the numerical linear algebra part of this course. So we will still see a lot of ideas like orthogonality occurs still furthermore in this course, but it kind of finishes off the numerical linear algebra part. Although we will apply it still. All right, what's the problem that we are considering now? We have a nonlinear system, so let me emphasize the non here. So we will still be doing a lot of linear algebra, but it is motivated by an overdetermined system of m equations in n variables. So we will immediately specialize this to 3 equations and 2 unknowns. So we will have a running example that's small enough, but it can scale to arbitrary dimensions. So we will solve it in the least square sense. What does that mean now? Well, what we did in the linear algebra problems, we had a residual vector, b minus a times x, where a is the coefficient vector, b is the right-hand side vector. Here we are minimizing the residual vector as well, but that is the vector of the function evaluations. One can interpret the vector of function evaluations as what you need to add to the equations. So assume that every equation has a constant term, what you need to add to those equations in order for your approximate solution to be the exact solution of the changed problem. So this is what it means, the backward error. This is a very, very general problem, and we will only solve this locally. So there may be many, many solutions here. So we have, in some sense, already seen this also when we did Newton's method. Also here, there may be many solutions, but if we make it overdetermined, that is often a method to have a highly nonlinear problem, make it have only one solution. So in a way, it looks like a much harder problem, but sometimes it's easier. The same as with the interpolation problem, we take more and more points, and they should be all mutually distinct to each other. So there is a best spacing there. But if you solve it in the least square sense, you can actually have some latitude there. Some points may actually be close to each other. All right, we have our Jacobian matrix again. So this is where the linear algebra comes in. So one can see the Jacobian matrix as a linearization of the problem. So geometrically, the Newton's method is the method of the tangent line. We will construct the tangent planes. And the construction of the intersection of the tangent planes will actually be defined by solving a linear system. So we have, in general, more equations, m equations in n variables. So we will have an overdetermined linear system. Then the method of Gauss Newton method is actually very much similar to Newton's method. So in a way, that this lecture comes towards the end of the first part in this course, close to the midterm, is also very nice because it allows us to recall many concepts that we started earlier on in the course, so Newton's method. So if you ignore all the fat letters, so I have the fat letters here to indicate that we deal with vectors, but we are doing the same move. So steps 1, 2, and 4 are the same. What is different is step 3, and this is where we are solving the an overdetermined linear system. So the A is the evaluated Jacobian matrix. The B is the right-hand side with a negative in it. So you take the negatives. So why that is, why do we have a negative here? Well, the same reasoning. So this is why this is now so good that this comes closer to the midterm. Why is there a negative? Well, check our derivation of Newton's method. All right, we actually see Newton's method here the third time. So check the Taylor series expansion. All right, so we will solve that third step. This is where we have the QR factorization coming in. In practice, we will see in Julia, we will be using the backslash operation. But everything that we have seen before, so the normal equations, the modified Gram-Schmidt and the Householder QR, they all apply to this setting here. So in a way, what is now the application? What is the running example? We look at the near intersection points of three circles. So we have three circles, one big one at the left, and then two mutually touching circles. And the solution is actually given already by the red point. And why is the red point closest? Well, here is where the orthogonality comes in again. So I'm drawing now here in blue the distances as good or bad as I can. So I have three orthogonal lines. So from the red point, I can go to the big circle and I can go to the little circles. So the red point there, it's actually close to a one variable problem, as the y coordinate has to be 0. So this is a very symmetric problem. It's almost a one variable problem. The formula, the formulation of the problem is actually now as an optimization problem. Again, with the first lecture last week, where we saw that if we are applying the optimization techniques. So if we are looking for the critical points of our objective function, we will actually end up with a linear system. Here I put it not as a equation of the polynomials, but really the distance. So let me explain why the expression at the bottom is actually formulation of the problem. We have three circles. X1, Y1 is the center of the first circle. The radius R1 is the radius. So what is here says that we want a point on the circle. So if it's on the circle, then it is 0. So if we look at one equation, then actually we have every point on the circle will satisfy this. But we have three equations. And the three circles are separate from each other. So we can see that there cannot be a real point and also not a complex point, not a real point that will lie on the three circles. So we cannot satisfy the distance of a point on the circle so we look for the coordinates x, y, so that we minimize the distances of the center of the circle with respect to their radii. Right, so this is kind of the setup. So it's a completely nonlinear setup, but we will solve this essentially with the backslash operator iteratively in what we call the method of Gauss Newton. So what follows next is the setup of this problem. So there is a Julia program on the website and also a Julia notebook. So we will do this as close as possible to the original problem formulation. So one could get rid of the square root and see this as a system of three polynomial equations and two unknowns. This will not be done here. We will keep the original problem formulation. So corresponding to the picture, we have coordinates. So we have the very big circle centered at -1, 0, radius 1, that's a unit circle. And we have two smaller circles that are touching each other. So the radius of those is 0.5. So we have the system here. We can formulate this with Julia with the SymPy package. So Julia recycles a lot of what is available in the Python ecosystem. So we will adjust what we did 8 years ago with the multivariable Newton's method, where we defined the equations now as 1, 2, 3. These are the names of the equations. In the Julia world, they will be entered as strings. We will use SymPy to generate functions that can evaluate the expressions as Julia functions, evaluate them as floating point values. So in a way, this is a modeling exercise as well. How can we generalize this? So you can see that this generalizes to any expression that can be handled with the SymPy syntax, which is very similar to any computer algebra package. I should also say, how does this problem generalize to any number of equations in any number of variables? Well, if you add one more variable to this problem, you're no longer interested in circles, but you may be interested in spheres. And then actually by adding one more variable, if you stick with 3 equations with 3 spheres, then it becomes again a fully specified problem. But if you add more and more spheres, then it becomes a fully again becomes a nonlinear overdetermined problem. And why spheres? Why this is a nice problem? Well, you want to see what is the closest point here that is at the closest distance to 3 centers. So this could be seen also as a computational geometry question. So in computational geometry, that's another course as well, one has the Voronoi diagrams for this. So in a way, if you think about generalizing this, would be another course. But in the fullest generality, we can actually define the setup here. Then what is the essence? So what was the step number 3 that I wanted to indicate? So let me get straight through it. So this is the update. This is here where the Gauss comes in. So Gauss is credited with the discovery of the least square solving to solve a problem in astronomical observations. One can read this about in the textbook or look it up online for the origin where Gauss comes in. The rest is actually recycling from lecture 13. So the slides have been kept to its bare essence, but we have here a function, 2 functions essentially. We evaluate the given system of equations. So here we evaluate x at x naught and y naught, 2 64-bit floating point numbers. So this is a fully numerical program, but with the aid of SymPy, we can define it in full generality. So we have made abstraction here how the functions are evaluated. So they are black boxes in this script here. Also the Jacobian matrix. The Jacobian matrix here is evaluated in one line. So also at x naught, y naught. It is the Newton step, and perhaps I should have written Gauss Newton step, but it is in full generality. So it works well in full generality, it works for 2 variables, but it is still general enough for any number of equations as well. So it's doing one step. It's returning the updated values. So here you see it updates x naught and y naught, and it returns the norm of the function evaluation. So this is the nfx here. This is a measure for the backward error, and then it also has a measure for the forward error. So this is the norm of the update. One would expect that for a converging process, the norm of the update goes to 0. And here we go. We do a run. And indeed, if we look at the coordinates, so this is what is printed out, we see that there is convergence. So the default tolerance was here 10 to the power minus 8. And we see that there is linear convergence. So we solve this problem with this global problem, starting actually from 0, 0. All right, let me take that in for, so let me so the arrow here points to the main question, essentially. Why so slow? In a way, you could say we're very happy with this result. So in a way, it's also a linear problem. So I started with y equals 0, and you can see that the y column did not change. So starting at 0, 0, we were actually solving a nonlinear least square problem in essentially only one coordinate x. All right, that's the run. Let's summarize what happened. So the backslash operator is a very powerful operator. So essentially, if you look at it from a syntax perspective, it's actually the same. The two methods are the same, but what goes into the backslash means that it's actually fundamentally closer. So why is it so slow? Well, it will be identically, Gauss Newton will be the same as Newton if we have actually an exact solution. So here actually we cannot really expect quadratic convergence, because remember, the quadratic convergence also is the close enough. So that's the reason for the why so slow. So it is in some sense the same, and you will see that in this course everything is this, the more we do different things, the more it is the same, but also the more we do it, the more it differs. So we give other names to the same things in some sense, and in a way Gauss Newton differs fundamentally from Newton's method. We have no exact solution. And this should not surprise us. We started with the least square, with the line passing through many different points. How can you make sense to this? Well, in some sense, it is a very well posed problem. Because we are asking a different question here. We are interested in only the least square solutions. So that has a unique solution. All right. Fine, then let's see if we can experience quadratic convergence. So this is an exercise where you have to modify or run and then observe. So in some sense, this is not a programming class where we do everything from scratch. We run, we observe, we explain. So what you will, and I can say that the answer to this question is quadratic. If one just believes the sentences of the previous slide. So in here, the picture shows that the red dot is actually now at 0. So here is also the fundamental difference if you change things. Start now here, start at 0.5. So 0.5 is actually quite far from the origin. So this problem is set up so that you're going to compute 0, 0. And you will observe quadratic convergence. Notice that this is similar to, you may have made that exercise in lecture 13, where we were intersecting two circles, and where the two circles are touching each other, it's going to be very tricky. And this is here, we are exactly in this tricky situation. If you imagine for a second that this large circle is not there, then Newton's method will not work very well, because it will probably still converge, but we have a solution of multiplicity too. Now, by throwing in the big circle makes this problem more complicated. But actually, at the same time, it makes the problem completely well conditioned. Because notice this, at the intersection point, if you would magnify this, I think I will not do this because I'm not trusting the environment, but magnifying it here, what you have the big circle, and then you have the little circles. And as I'm trying to botch this picture here a little bit, so this is magnifying out. You see that the big circle and one of the little circles, they actually intersect orthogonally. So locally, this looks very much to solving a system where the coefficient matrix is orthogonal. So this three-circle problem has a very, very nice conditioning. It might also, and this is now making the transition to the next step. If you look at the column space of the matrix, so if you would look at that, you can see how actually looking at this, the over-constrained problem regularizes the problem. Let me try to explain this now. So with the singular value decomposition, in a way, if you have seen a linear algebra course, then the singular value decomposition should be familiar to you. But let me define it in the numerical analysis sense. So it's yet another matrix factorization, and it is a diagonalization. So we've seen that with the eigenvalues and eigenvectors, we can diagonalize a matrix and we can do this actually in general, but so the eigenvalues and eigenvectors give you a diagonalization that is nice to compute if all the eigenvalues are different from each other, none are 0. So no multiplicities, no singularities. The single value decomposition, so the word says it, what you actually compute are a sequence of singular values on a matrix that typically has fewer columns than rows. So the two utmost important properties of the singular value decomposition are that it generalizes the QR decomposition. It gives more information. So the QR decomposition, as you like with a picture, you can see that it reduces the matrix to a triangular matrix, an upper triangular matrix. And mean that upper triangular matrices we can solve very well. So the QR factorization does this. The singular value decomposition provides a diagonalization of the matrix. What it does, it also defines the numerical rank of the matrix. We can define how close the matrix is to a singular matrix, even for matrices that are not square. So the inverse, one can also define a more generalized inverse to that. We will not do this, but here we have the two most important properties of the singular value decomposition. The diagonal with the singular values is the most important result there, but you recognize there are two orthogonal matrices, and the orthogonality is again referring to the numerical stability for the algorithms that are applied to computing the singular value decomposition. So in a way, you could see that it generalizes also the QR in this sense. So we do, with the householder reflectors, we are multiplying to the left. And we multiply also to the left with this U matrix, but we also multiply from the right now with this V matrix. So in a way, you could see here this equation as a diagonalization method. So we have interpreted the QR factorization. So the matrix Q, with the modified Gram-Schmidt, the matrix Q contains the orthogonal basis representation for the column space. In the householder QR, the Q is the matrix of transformations, Q transpose. Then what you need to do on the matrix to reduce it to an upper triangular form. The U can be seen as the equivalent to the Q, but there's also a V that is there, also an orthogonal matrix. So from an algebraic perspective, we do more reductions. In a geometric perspective, this is where in the geometric view, this is where the numerical rank comes in. So the singular values are sorted from large to small. And we are cutting off after a certain threshold. So singular values that are small are ignored. So that actually means that certain columns in the matrix, if you then reformat, so here we have this other problem again, if you cut off the smallest singular values, you actually find a matrix that is close by to the given matrix, but that is a matrix with a given rank. So geometrically, the singular value decomposition projects the given matrix into the space of all matrices of a certain rank. So there is a lot of many words, I mean, perhaps not too many words, but the two important properties kind of have the algebraic aspect in the factorization and also the geometric aspect of the singular value decomposition. All right, this is so the previous slide was extremely abstract, and now let's make our hands a little bit dirty and do some computations. We generate a small 3x2 matrix, and then we compute the SVD, the singular value decomposition, via the SVD command. So with a 3x2 matrix, everything fits on one slide. So we see the singular values. We see the U factor and the V factor. And it's actually interesting to see that what I said in the previous slide is already a little bit confusing, because the U is now a 3x2 factor and not a 3x3. This has to do with the way it is implemented. The single value decomposition is actually computed. But let's not confuse ourselves too much. Let's see if we can still verify the essential properties of the Julia, of the singular value decomposition. Well, the singular value decomposition allows us to reconstruct the matrix. So it's in factorization. So if you do U times the diagonal parts times the transpose, you actually have this equation here. The equation, the factorization property, while underlined in red, is translated into Julia in this command. And then perhaps I should use another color. So we have then the diagonalization property. So what I'm now trying to underline in green is also translated in that command. So I spell out the transpose in full, but one can use the prime symbol to write it shorter. But primes are often overlooked, and that's why transpose is perhaps even better. You see that we read our numbers from right to left. So this is the diagonal matrix. So again, it doesn't look like, and if you are not familiar with numerical analysis, then you would say, well, wait, this is not a diagonal matrix. But look at the scientific notation again. We see that on the off diagonal, we have close to machine precision numbers. All right, then. Let's now go back to the output of the singular value decomposition. So importantly, how did this now regularize this problem? So why is this a good problem? Well, we have three equations and two unknowns. So the Jacobian matrix is a 3x2 matrix. And if we are computing the singular values, then the two singular values are very, very far from zero. So they are a healthy looking 1.5 and 0.9. So this is a well-posed problem. So this is an after-the-fact verification of our intersection point. So we do one more verification step. So the 10 to the power 9 might not reassure us that much. It actually says that we have so this is, well, it is reassuring. We have about 8 decimal places correct. Now, but the 8 decimal places, if you did the exercise with the 2 touch circles, that was actually not very good. So because we like to expect 16 decimal places. Now, the singular value decomposition shows that this is probably the best you can do. It is a regular problem. But the reason why, again, we don't get anything better out of this, because there is not a unique exact solution. So that's kind of the best we can do. So going back to the exercise, the previous exercise, the 2 touching circles and the pick circle, if you dare look at the Jacobian matrix, please do also do that verification step. Then actually you will see that there you have a very nice regularization of the problem. All right, then. That was one application. Here is the other application. It's a definition of, so a better definition. So we had the mathematical formulation where we derived in the case of a regular square matrix. So here we had the assumption that the inverse of A had to exist. So this definition makes then perfect sense for a square matrix, but it doesn't make sense if your matrix is not square, or if your matrix is square but there is no inverse. Then of course you can still solve the problem as we did with the Gauss Newton, but why is it now well posed and well conditioned? Well, you can look at the singular value decomposition. So the condition number, and this is here the proper condition number of the least square problem of the matrix. I'm sorry. So again, this is not completely correct for the least square problem, because the right-hand side vector also plays a role. But for the matrix, one can define now the condition number as the largest condition number, as the largest singular value over the smallest singular value. And this is provided that the kth one, so we have k columns, is not zero. If it is zero, what do you do then? Or if it is close to zero, you cut off at the threshold. So this is a very adaptable definition. Notice there are two numbers there. This number will, so when is the condition number large? It will also be large if your first condition number is large. So, and this captures the case when you have very, very large numbers in your matrix. The denominator captures when your matrix is close to being zero, close to being singular. So in a way, you notice that in a linear algebra course, you may have talked a lot about determinants. Here, actually, we don't really talk about determinants to capture the singularity of a solution. We look at the singular value decompositions. All right. How do we do this now again? We had the command, the Julia command. How is this now actually be done? Well, let me illustrate this on a very small example, 3 by 3 matrix. We compute the condition number, which is very nice. So the condition number is 7.3. We compute the singular value decomposition and take the largest singular value over the smallest singular value, and you can see that the output coincides almost exactly. So isn't that nice? So we now see how the command to compute the condition number is actually a wrapper over the singular value decomposition. All right, and I'm actually running a little bit behind. So here we had the running example of the entire sequence that we have solved already many times. So we solved it with Gram-Schmidt, we solved it with the Hausholder QR, we did it with the backslash. Backslash is, by the way, the shortest way to solve this, but let's now also solve this with the least square sense. So this is another factorization that turns the linear system solving into a diagonal system. So here are the formulas. So actually here it is. You will solve a diagonal system by computing this step. So you compute first the singular value decomposition. Just like with the LU factorization, we have an auxiliary vector y, which is the solution of this step. And then we do one more step. So it's a two-step process, just with the LU factorization. After the factor, so it's actually a three-step process. So we do first the singular value decomposition, and then we use the S, the U, and the V. The S and the U are used in the first step, where we solve a diagonal system, and then we do matrix vector multiplication. So we have to do a lot more work in the first step. So the singular value decomposition is quite expensive, but we save a lot of time in the next steps. And the singular value decomposition solves in the least square sense. That's the punchline of the title of this slide. And it gives you actually much more. It gives you the numerical conditioning as well. Okay, I have 5 minutes for the method of Levenberg-Marquardt. We've seen the very slow convergence of the Gauss Newton method. Now, you could also say that this is because we were still very, very far from the optimum. So one can, when very far from an optimum, so this is now going back to the very early beginnings, we actually have an optimization problem. Please then apply methods of optimization. So if you are very far from an optimum, the gradient will provide most information. And when you get very close, the influence of the Jacobian matrix will matter most. So we are having now a hybrid, and that's the essence of the method of Levenberg-Marquardt. We are introducing a parameter lambda via the normal equations that will interpolate between the method of Gauss Newton, where we look only at the Jacobian matrix, or where we place the heaviest weight on the Jacobian matrix, or in the opposite direction, where we look mostly at the gradient. And the update formula is actually formulated here. So it's also a one-liner, just like with the Gauss Newton method. That's actually why I can still afford to explain this method in 2 minutes. What I just highlighted here is the essence of the method of Levenberg-Marquardt, where the infinity is kind of a little bit a value that you should never take. The exercise will invite you to explore good values. The normal equations are quite good to use for small, well-conditioned problems, and with the Cholesky factorization, we have the very fastest method for small problems. This is a convoluted exercise, so we can make random square matrices with prescribed condition number. Let's then experiment with the condition number. So in a way, I introduced the method of Levenberg-Marquardt as very far, geometrically very far, very close. But you could also see this somehow as improving the condition number. Solving the normal equations is not very good because it could be badly conditioned. Now, well, you make it diagonally dominant. So that's actually what this exercise explores. So you add a multiple of the diagonal to it, and you will get better and better conditioned matrices. So it is an improvement of the conditioning. We ended last lecture with this. Now, how do we get to the Levenberg-Marquardt? Well, we do it as the very beginning. So in a way, there's nothing new. So the more we do other things, the more we do the same. So here we look at the optimization problem, and we take derivatives to solve the least square problem. And you will see that when we do the computation of the critical points, we end up with the formulation of Levenberg-Marquardt. We actually have the product of the gradient with the right-hand side. And that's what the steepest descent is. So I'm at the end of the lecture. I'm ending with the method of Levenberg-Marquardt, which is an iterative method where the main difference or the main similarity is again that we apply the backslash operator to what I just underlined. So here is one exercise. So there is a Jupyter notebook that is posted that will actually define the nonlinear Gauss Newton method, and there is adjustments that you have to make to implement the method of Levenberg-Marquardt, and then I'll run it on the three-circle problem. All right, 4 lectures. It is a geometrical problem related to constructing an orthogonal basis for the column space spanned by the coefficient matrix. The classical Gram-Schmidt method is another example of a numerically unstable method, similar to LU without fitting, but the modified Gram-Schmidt method is numerically stable, doesn't lose orthogonality. The householder QR is unconditionally numerically stable. It's the method that is applied when your matrix may have linearly independent or close to linearly independent columns. We've seen the generalized minimum residual method. That is an iterative method that applies the least square solving to smaller problems, taking a selection of the columns of matrix. And we finished with several combinations of methods, the method of Gauss Newton and the method of Levenberg-Marquardt, combining again ideas from optimization and linear algebra. So I'm running out of time, so I will stop this recording.